Okay, now we have learned on the steps in finding stationary points and using a Hessian function to find the nature of the stationary points. Let's try to apply it again in exercise 5.8 by finding the stationary point for these functions and also determining the types of these stationary points by using, of course, the Hessian function. Alright, so this is the function. Okay, first let's find the stationary point. To find the stationary point, again, it talks about the slope that is equal to 0, or you can imagine a horizontal line on the graph. So when it say that the slope is equal to 0, it also means that the partial y and partial x for this function, the first derivative, partial first derivative for this function, should also equal to 0. So that let us write that down. Okay, so partial f over partial x equal to this function, and it should be equal to 0. Partial f over partial y is equal to this function, and it should also be equal to 0. And let's name it as the first function and the second function. So by using this equation, we are going to look for the stationary point, right? The stationary point which consists of x and y. I'm using the first function as the starting function in finding x and y, so I can deduce this to it to become in terms of x. So x is equal to negative y minus 5 over 2. That is the best that I can come out with this function, but never mind. So let's just substitute this into the other function. So any x variable will be substituted with this function, right? So we have this that will be substituted later. So this we have substituted, and we tried, because of this already, we already reduce it to one unknown variable, which is y. So let us solve for y. So I get y equal to 5. Basically, I already get y, which is equal to 5, but still x is in terms of function, but there is no problem because I can just substitute y here, 5, into this function x to get the value of x. So by doing that, I get this point, negative 5, 5. In other words, for this function, it only consists of one stationary point, right? You can also imagine that that function only consists one horizontal line, right? One slope that is equal to 0, one line of slope that is equal to 0, or there is no slope, right? So one point only. Okay, so we have already figured out this stationary point, and the next thing to do is to find out the nature of that stationary point, whether this slope is a kind of turning point, or maybe it is just a saddle point, right? An inflection point, right? So to find out the nature, again, we are going to use the Hessian function. To calculate for Hessian, we'll need to first be prepared with the second partial derivatives, all of the second partial derivatives. Okay, we have the partial derivative of x, the partial derivative of y, and also the mixed partial derivative. Alright, this is all of the derivatives. And I want to emphasize again, your mixed partial derivative can be x to y or y to x, right? It is the same. Okay, now that we have this, we can input everything in the Hessian function. So this is the Hessian function, right? The partial the second partial derivative of x times with the second partial derivative of y minus with the mixed partial derivative squared. So the answer is 3. So 3 is more than 0. So what can it, when it is more than 0, right, we need to look at again the value of each second derivatives of x and y. If it, for this case, it is both of them are more than 0, so we can conclude that this point 55, negative 55, is a stationary point that actually on the bottom of a graph, right? You can imagine that this function, right, going downward, and then it will lay flat at the end before going back upward. So during this turning point, this is where the slope is equal to 0, and this is where the point is, negative 5, right? So that is for this first question. It contains a minimum point. Now let's try to look at the second one. Right, we're going to do the same thing. Okay, so this is the question. Right, the first step will be finding the first partial derivative of both x and y. Okay, so this is the first one, this is the second one, and then I'm using the second derivatives because it seems like it will be a lot more simpler compared to the first one, and I end up getting x equal to y, right? Then of course substitute this function into the other function that you have here. So I substitute all of x here to y, right, based on this, and I obtain 2 value of y equal to 0 and y equal to 4/3. Okay, because of x equal to y, whenever y equal to 0, x will also equal to 0. Whenever y equal to 4/3, x will also equal to 4/3. In other words, for this function, we have 2 stationary points, which is this. Okay. Now let's determine what are the natures for both of these stationary points. Okay. To determine the nature, we are going to use Hessian function, and to use Hessian function, we need to proceed in finding all of the second partial derivative. Okay, so this is what I get, the functions for the second partial derivatives, x, y, and mix. Now let's test it with both of these points. As you can see, at point 0, 0, when we substitute it in the Hessian function, I get 2, which is more than 0. So because of it is more than 0, I will need to further look at the second partial derivative of x and y, and I noticed that both of this value, when being substituted with this point, is equal to negative value, which is less than 0. So when it is less than 0, right, we can conclude that this point is at a maximum point. In other words, this point is the highest point compared to other point in that graph. So we can imagine that a graph from below going upward, and then we have a turning point here. So on the turning point here, we have stationary point 0, 0 that lay flat here, right? Slope equal to 0, 0, remember? That is where point 0, 0 is. Now let's look at the second point, which is 4/3 and 4/3. So substitute it into our formula, Hessian function, and we get -8, which is less than 0. So because of it is already less than 0, we don't need to refer to the other second derivatives, right? We can just come to the conclusion that it contain the location is at a saddle point. It is being considered as a saddle point. So what is a saddle point again? Saddle point is the opposite of turning point, right? Saddle point, let's say if a graph come from the bottom going upward, when it reach this point it will lay flat, right? Because slope equal to 0, right? But then after that stationary point, it will go back upward. So it is not turning down. The same goes to if the graph come from the top. It will go to the bottom and then it will come across this point, right? And lay flat. In other words, slope equal to 0, right? And then it will proceed to go down. That is what is meant by saddle point or inflection point, right? So that is both of the point that we're able to figure out, and that is actually the step in in finding stationary point and later finding the nature of stationary point by using Hessian function. And that's it for this chapter. Thank you guys. Bye.